We have another question which is now on energy principles, work, energy and power as well, and now we're going to be tackling that one. Remember how we do. As we are working, I'm going to elaborate on the question, show you how to answer the question, tell you what the examiner is actually expecting from you, and what you should actually be doing in this question. Also telling you where your marks actually come from and so forth. So please grab your notebooks and let's start. So the next question that I have from us, it is from Apane Andina, and they say that a pendulum. Now let's just elaborate on what is a pendulum first. So pendulum is something that just like moves back and forth and swings and so forth, right? We actually, growing up, we also had these pendulums that you'd put, there's like 4 of them and one would bounce and then it would bounce on the other one. And it actually is a good way to explain Newton's laws. But in this case, we've got a pendulum with a bob. Don't let them confuse, not bob meaning short hair, but a bob meaning the circle here at the end. With a bob of mass 5 kilograms. Something interesting is that they already gave you the mass in kilograms. Most of the time, they'll give you the mass in grams. If the mass is in grams, that is not the correct SI unit used in physical sciences, so you have to convert it to kilograms. SI units learned in grade 9, you must know it. It is held stationary, some terminology for physical sciences. Scientists are really lazy people. We don't like saying something is standing still or something has stopped and so forth. We just say stationary. If something is stationary, it means the initial velocity of that object or source is then 0. Stationary means not moving, no velocity. Initial velocity is then 0. It is at a height which is h meters above the ground. Now already when you're seeing above the ground and so forth, I want you to think potential energy, kinetic energy and all that stuff. When released, it collides with a block of mass 2 kilograms, which is also stationary. What did we say? Something that is stationary means there is no velocity at point A. The bob swings past A and comes at rest momentarily at a position a quarter of h. Now think about it. We have h, which is h here, and only a quarter of h's height does the bob actually come to a rest above the ground. The diagram below are not drawn to scale. So let's look at what's happening here. Here we've got a before, we have an after. Now before, we can have potential and kinetic energy. So at a certain height, we have potential energy. So we've got EK, which is 0 because there was no velocity at this point. We've got EP, which is potential energy. There is a certain height there, so potential energy does exist. It's then let go and it starts swinging and it hits a block. Again, here we have a block which is stationary. It's not moving. And then after we have height again, we've got velocity and the block is also moving. Before and after, you must keep that in mind. The block was stationary here, so initial velocity was 0. The block was also standing stationary before it collided with the block, so initial velocity is also 0 there. Let's see what the question continuously says. Immediately after the collision, the 2 kilogram block begins to move from A to B at a constant speed. So all the way from here, all the way there, it moves at a constant speed of 4.95 meters per second to the exponent 1. That is now the velocity it moves in. So initially it was 0 and then it starts moving with a velocity of 4.95. So we can assume that this for now could be our final velocity, depending on the question. We must ignore frictional effects and assume that no loss of mechanical energy occurred during the collision. Now, when they talk about loss of mechanical energy, remember we talk about elastic and inelastic collisions. So 5.1, we are told we must calculate the kinetic energy of the block immediately after the collision. Kinetic energy, remember, the block is standing at a certain height and it will then move down immediately after the collision. Meaning the block was standing stationary here. After it collides, what will the kinetic energy of this block be? Take into consideration, this block was standing still. All of a sudden, this block moves with a velocity of 4.95, which means that even though the bob was initially there, when it was released, it moved with a velocity of 4.95, which made the block move with a velocity of 4.95. So now here you had to be quite strategic and think like a scientist that this block cannot just be moved by any air or frictional forces or whatever. It means that this bob here made it move by this velocity, which means that this bob over here acquired or attained a velocity of 4.95, which made this block move with the same velocity. This was for 3 marks. It is actually an easy question, but if you didn't really know how or what made the block move, then we were not going to get it correct. So the first question, which is 5.1.1, we're looking for EK. Remember, you always write a formula in physical sciences because you do get a mark for that. Kinetic energy after the collision is 1/2 mv squared. Remember to always put brackets around your stuff. We are told that the bob has a mass of 2, which is 4.95, and that is then squared. Let's put this in my calculator and see what we get. 0.52 and 4.95 squared. So here I'm going to get 24.50. If the 2 was 5 or greater, it would have changed the 0 to a 1. In this case, only 2 decimal places in physical sciences or in chemistry. So it's going to be 24.50. 24.05.50, sorry. The SI unit for kinetic energy is a capital J for joules. Therefore, now we've calculated the kinetic energy of the block immediately after the collision. Now we have to calculate the height at h, right? We need to find out what is the height here at h. Now, there are 2 ways, or probably more ways of doing it. I can only think of 2 ways. Calculating it at h, you need to think of, am I going to use the fact that my potential energy, let me just erase all of this. Am I going to use the fact that my potential energy changed to kinetic energy, meaning EP here will be equal to EK on this side. Initially, the ball had potential energy, which then was converted to kinetic energy. So EP is equal to EK. Or am I going to say mechanical energy before is equal to mechanical energy after? What does that mean? Initially, we had velocity, which was 0. However, we had height. At the block, we also had initial velocity, which was 0. After, the block actually started moving, and the block also had a height. So you can think of it in 2 ways. I'm going to show you how to do it in 2 ways. Let me see if I've got to have space. Okay, let me do it here. So this will be 5.1.2. I'm going to show you in 2 ways. So the first thing, let me just write a note here so that you know. Remember, first it was at a certain height, so we know that the loss of potential energy of EP, the loss of potential energy of the bob, is equal to the gain in EK. It had potential energy at the top, it hit the block, started moving, and then it had kinetic energy. Therefore, I can say that mgh, which is EP, is equal to 1/2 mv squared. Remember, they are looking for the height at h. Be careful in what the question is saying. They're looking for this height and not the height 1/4 of h. They're looking for the height at h. That's what the question asked for. So I know that the mass of the bob is 5. At a certain height, anything that has a certain height or above the ground has got gravitational acceleration. The gravity will pull everything with 9.8. We are looking for the value of h. I'm going to have 1/2 on this side. The mass of the bob is 5, and we have already calculated. On this side, we've actually already calculated the kinetic energy here. So I can just write my final answers here, which is 24.50. Right? This is the answer that we got here. The kinetic energy of the block is the same kinetic energy of the bob because that is then what made it move. However, now we must be very, very strategic with what is about to come next. Remember what the question is saying. We must calculate the height at h. However, whatever h is, the ball was 1/4 of that height from h. Right? I'm going to show you from grade 9 mathematics, more or less. Remember, in grade 9, we were told if you want a whole number, for example, if I've got 1/4 and I want to get a whole number, meaning 1 or 4/4, I'm going to say 3/4 And if your numerators are the same, you can add your denominators. 1 plus 3 gives you 4. 4 over 4 gives you 1 whole. So now if it was a height of 1 over 4 after the collision, it means that height of h, even though this was a quarter of height of h, it means I am at 3 over 4 of that certain height, right? So I'm going to use 3 over 4 for h. Let's go back here. So I'm gonna do it the long way around. I'm gonna have 5. I'm gonna have 9.8. I'm going to have 3 over 4 of h, right? And this is 24.50. Remember, 24.50 is the kinetic energy of the block. We use it the same as the bob. Now it's just mathematics. I'm going to put it exactly as it is in my calculator for the first part. Remember to always put your things in bracket. You're going to have 9.8. You're going to have 3 over 4. Put a bracket around that one. Therefore, I have 36.75 h. Don't forget the h. 36.75. You have an h on that side, all equal to 24.50. However, I am looking for h alone, so I'm going to divide both sides with 36.75. What you do on the one side, you do on the other side. This and this will cancel, and then I'm going to have h on the side. So I'm going to divide 24.50 divided by 36.75, and therefore I get 0.666666. Remember, in physical sciences, always to 2 decimal places. If the third number is 5 or greater, it will change the number before it to its nearest number. Therefore, it is 6, so the 6 will change the 6 in front of it to a 7, giving me a height of 0.67. 0.67, remember, the SI unit for h rather is, when we talk about height, we talk about meters. So that is one way you could have done it, right? Knowing that a potential energy changed to kinetic energy. Another way you could have looked at it, you could have used the mechanical energy principles to say mechanical energy before equals mechanical energy after. So you could have said ME before. Now remember we are talking about two different objects, will be equal to the mechanical energy after. Now remember what happened before. Before, we know that we had potential energy, which is mgh, plus kinetic energy, which is a half mv squared, equal to. After, we also had mgh, plus we also had kinetic energy, which is a half mv squared. Now let's listen to the story. Initially, the bob was at a height, that is the h that we are looking for. The mass of the bob is 5. The g is gravitational acceleration, and gravity will always, or we use a 9.8 in grade 12. I'm looking for h plus. What were we told with the kinetic energy? We were told that initially the bob was stationary. Where were we told here? There we are, that the bob was stationary. Now remember, if the velocity is 0, if v is 0 here, everything else becomes 0. So I've got a 0 here, equal to. Now I know that after the collision, the bob still had a certain height there, which I still don't know. So therefore the height is not 0 because it still had some form or sort of height amongst it. The mass was 5, g was 9.8, and then I'm looking for height. But what was I told? The height was 1 over 4 of that height, which was then h, plus a half mv squared after the collision was the kinetic energy of the block that we got here. So I'm still going to use the same kinetic energy, which is 24.50. So here you needed to be strategic. You needed to remember that the kinetic energy we calculated here for after the collision will also be used over here. Now we're just going to do simple mathematics. We're going to do it step by step so that everyone understands where I come from. I'm going to say 5 times 9.8. Here we're going to get 49h. 49h on this side equal, I'm going to put that in my calculator as it is. On this side, I'm going to get 5, 9.8, and then I'm going to have 1 over 4. Let me just put that up there again. There, 1 over 4. And then I'm going to get 12.25. 12.25. Please remember your h, my darlings. Plus 24.50. 0.50. Now, mathematics. I'm going to put all my like terms on the one side, and I'm going to leave all my unlike terms on the other side. I've got H's on this side. This one and this one is a like term, and then this one here does not have a friend. I'm going to take the 12.25 to the other side. So I'm going to have 49H. Remember, if it is a positive on this side of the equation sign, if it comes to this side, it becomes a negative 12.25 H, all equal to 24.50. See what we get here. So I'm going to have 49 minus 12.25. I just forgot a 25 there. There we are. So I get 36.75 H. 36.75 H, still equal to 24.50. Remember, I'm looking for the H. I'm going to divide both sides by 36.75. What you do on the one side, you must do on the other side. This and this will cancel. So H will give you, we should get 0.75 exactly like on this side. If I say 24.50 divided by 36.75, see what we get. Voila, we get 0.67. Remember, if the third number is 5 or greater, it rounds off the number before it to the nearest number. This 6 will round off this 6 to a 7. Chemistry and physical sciences, we always use 2 decimal places. So that will be 0.67. The SI unit for H will then give me, or is M. So that is the 2 ways you could have looked at it. Way number 1, which is this one, you could have said the loss in potential energy is the gain in kinetic energy, which for me sounds much more easier. Remember, if the ball after the collision was 1/4, it means that H was 3/4 of that because it lost a certain height. And then I was able to find my H. Or you could have used the mechanical energy principles to say mechanical energy before is equal to the mechanical energy after. You also just needed to remember that it was stationary. No velocity means this was 0. The change or the kinetic energy of the block after the collision is what we used here. If the block was able to move at a certain kinetic energy, is because the bob's potential energy actually made it move with that kinetic energy. Remember, energy principles. Energy cannot be created or destroyed, but it can be changed from one form to another. That is why a loss in potential energy is then a gain in kinetic energy. So now we've calculated the H and F, and that was then for 4 marks. Remember to show your examiner everything, all the steps, all the formulas, and so forth. Now we're moving to another part of this question paper. So now we are told that the block moves from B. Let's just make some space for new stuff here, because now we are continuing with something else. So we're told the block moves from point B at a velocity of 4.95. So, it moves from here. It moves from a velocity of 4.95 meters per second. And now it's going up. Remember, the minute you hear up an incline or up a ramp, you must already think vector diagrams and so forth. Up a rough. When we talk rough, we talk about friction. We talk about forces opposing motion and all that stuff. Up an inclined plane to point C. The speed of the block at point C is 2 meters per second. I can see that my speed is decreasing. We had 4.95 meters per second here. It decreases to 2.2 meters per second, And at point C, which is 0.5 meters above the horizontal, as shown in the diagram below, during this motion from B to C, a uniform frictional force acts on the block. Right, so here we've got the block. After it was hit by this bob, it continues to move, and then it starts moving up a rough incline, and friction says, no, you're going down. Friction doesn't want it to move up, right? It is at a certain height as it moves up. So really the examiner, or this question paper, is giving us a clue on how we actually should be answering this question. Because 5.2 says we must state the work energy theorem in words, and that is then for 2 marks. We must state. I cannot stress this enough. If you have to state, if you have to define, if you must name a principle or a law in physics, it always stays the same. You are not explaining to the examiner what you think you understand or what you think is right. A definition, an explanation, and having to state something always remains the same. So we're gonna state the work energy theorem. I'm gonna show you an easy way on how to remember it so that for tomorrow's exam, my darlings, you don't have to stress. Remember it exactly as how we did it here. So for 5.2 is the work energy theorem. We say the net work, remember net is just a fancy word in physics. That means the same as total. So the net or total work done on an object is equal to the change in the object's kinetic energy. Now remember what I always say in physical sciences, there's a formula and definition for everything. Remember we have a formula that says work net is equal to change in EK. Now let's elaborate on what this means. W is work. I'm going to read from here and elaborate on this definition. The work net or total work done, remember net just means total, on an object is equal to, here's the equal to the change. In physical sciences, when we say change, we use the symbol here. We call the symbol delta, but triangle means change. Right? We change in velocity, change in acceleration, and so forth, is equal to the object's change in kinetic energy. The type of energy we're talking about here is EK. So the work net is equal to the change in the object's change in kinetic energy. You cannot get it wrong. Remember what I always say, there's always a formula to remember something or everything in physical sciences. Remember to always find easy ways to actually help yourself remember your definitions, your structures, and so forth. So now for 5.3, we are told we must use energy principles, work, energy, and power. We must use energy principles to calculate the work done by the frictional force when the 2 kilogram block moves from point C to B. Now remember, friction is a non-conservative force, and these types of forces actually take away from the system. These are non-conservative forces. We must calculate the frictional force that the 2 kilogram block does from point B to point C. So let's see what we have here. So here we've got 5.3, right? Just want to redraw this one for you so that you know where it's coming from. They did say a rough horizontal surface. I am told that it has a height of 0.5 meters. Initially, remember, it moved with a velocity of 4.95, yes, meters per second. Now, we are told that the system here is then rough. Now, just to elaborate on this further, some of you guys actually, strong points is when you use like FNet and so forth. If you do want to use FNet, you're more than welcome in using it. They did say energy principles. If you feel comfortable with using, calculating the frictional force or using the non-conservative force formula, then you're more than welcome. Always remember to have a formula. And always remember when you're talking about the energy principles and stuff, when do we use cos of 0 and when do we use cos of 180? When we're talking about friction, remember friction will oppose motion. Initially when we use Newton's laws and we use Fnet and so forth, then we'll just put a negative to show that the vector diagram shows that the one is going in this direction and the other one is going in that direction. And from physics, we know that vectors in opposite direction means that we need to subtract them. However, when we're doing work, energy, and power or energy principles, we don't really put a negative. We then rather use cos of 180, which is -1. The examiner wants to see that you know that cos of 180 means we're going to get a -1. Those are the nitty-gritties that the examiner is kind of looking for, so do not make those mistakes. So this is our structure that we're looking for. We're looking for the work done by the frictional force. I'm going to show you two ways in which you could have approached the question, and then I'm going to show you how you can do the question. So you could have used work net. This one is an easy one because remember, we were asked that definition. Let's see if we can use this formula to answer that definition. The work net done, the total work net or total work done on an object is equal to the object's change in kinetic energy. They already got the definition for work net in my head, two marks into the bag. So you could have used this one. Now remember, the work net of a block that's going up, I know that if I had to draw my diagram, I would have my friction moving in the opposite direction. I would also have my FG parallel that is also moving the block down. So the total work net, or the forces working on the object, will be the work done by the frictional force plus mg delta y cos theta, which is equal to change in EK. Another way that you could have approached this question, now remember there's many ways of doing it. You could have said the work done by the non-conservative forces. Just want to stress on this because they like asking you what is non-conservative forces. So these are forces like friction and air and stuff, air resistance. And remember that when you talk about non-conservative forces, these forces, they take energy. They take energy away from the system. Now already we can see that it is taking energy away from the system because initially it was moving at a velocity of 4.95, but we are told when it reaches point C, it moves with a velocity of 2, if I'm not mistaken. It moves with a velocity of 2 when it gets to point B. You see that the energy, it actually takes away from the energy in the system with 2 meters per second. But anyways, having to use a non-conservative force, let me just rewrite it here. The work done by NC, non-conservative forces, is equal to the change in EK plus the change in EP. So you could have used any one of those. I'm going to use this one because I know that at the bottom, no potential energy, but we have kinetic energy and so forth. So I'm going to use this method of articulating this problem. Now remember, non-conservative forces, I'm going to do it step by step, so please do stay with me. In kinetic energy, I know that it is a change in kinetic energy, so I'm going to have kinetic energy before and equal to minus kinetic energy after, so final minus initial. Remember, initially the block moved with a velocity of 4. The final velocity it had was 2. So I'm going to say 1 over 2m, this is what is common, open bracket, Vf squared minus Vi squared, plus, I'm going to have potential energy. What is common is my mass. Let me not put brackets for now so that I don't confuse you. But I've got mg, which is common, but my height changed. At point 1 here, I had no height. But at point C here, after, I did have height, which was 0.5. So I'm going to have h final minus h initial, right? It is a change in kinetic and potential energy equal to. Now I'm going to plug in what I'm given. I'm going to have 1 over 2. My mass of the block is 2. I'm going to open a big bracket. The final velocity at C was 2 squared minus the initial velocity that the block moved from up the ramp was 4.95. 4.95 squared, close my bracket, plus the mass is 2. Gravity will be 9.8. Open a big bracket. The final height was 0.5 at point C. But the initial height that the block had here, it was on the ground. This was before it went up the ramp. There is no height here at point 1, so my initial height was then 0. This is my sum. I'm going to put it in my calculator exactly as it is. Let's see if we do get the correct answer. But now remember, if you think you doing it like this will give you the wrong answer, then don't. But I think to be on the safe side, let's break it up. I'm going to do 0.5. I'm going to do the change in kinetic energy first, 0.5. And then I've got 2. Open my bracket. I'm going to have 2 squared minus 4.95 squared. Close my bracket. I'm going to have 20. You know what? To be on the safe side, let's write everything because the more you round off, it doesn't really give you a correct answer. So that's 20, 50, 25. So that's negative 20.5025. Let's do the other part. Now we're going to do the change in potential energy. I'm going to say 2, open bracket, 9.8. Close my bracket. Final height was 0.5 minus initial height is 0. I don't have to put the 0. There's no squares in this one. And then I've got 9.8. So I'm going to plus 9.8 in my calculator exactly as it is like this. I'm going to put it in. So it's negative 20.50, 25, 50, 25, plus 9.8. Just go back, 9.8. So I get a negative. I get a negative 10.7. The 2 is 5 or less, so it does not change the 0. So that will be negative 10.70. Negative 10.70. That's the work done by the non-conservative forces. The SI unit for the non-conservative forces is then a joule. Now remember, friction is a non-conservative force because it does take energy away from the system. Now remember what happens. Friction always opposes motion. We are told that this block is moving up the ramp, but friction says, no, 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 come back down. It's moving it, it's opposing it. That is then why we have a negative 10 to the 7, 0. Was this our last question for this one? Yes, this was our last question for work, energy, and power principles. As you can see, when you attack such questions, I always say, work on your paper, draw the structure if you need to draw it again. Remember all your things about your non-conservative forces, frictional forces, and so forth. When do we have a negative and all that stuff? And then as you're working it, make your notes if needs be, because the foundation of the whole terminology of the whole physics is what's really going to help you answer all these questions. But now that we're done with work, energy, and power, I think let's go for a quick ad break, and when we come back, we're going to do a little bit more revision on paper number 1.